Hello everyone, I'm Dale Jackson, and today I'll be discussing with you DC offset circuit analysis. We have a basic DC offset circuit here, and what we'll do is we'll have our DC voltage source offset our AC voltage source at our point here V out by a certain set amount. So we have R1, R2, and R3 here as resistances, and we have a capacitor there to couple the AC. So this type of a circuit has two different analyses. It has a DC analysis and an AC analysis. And what we'll do is we'll draw two different types of sub-circuits to see the type of effects that the DC or the AC has on it. So to start with, we'll take a look at our DC analysis. And draw a sub-circuit for that. So one explanation to why we drew this sub-circuit to look like this, notice that I omitted R1, I omitted C, and I omitted VAC. The reason for that is that a capacitor is going to be open to a DC source. And here's the reason why. Because the capacitance, the impedance of a capacitor with respect to frequency, because a capacitor is frequency dependent, is going to be 1 over SC. And in terms of frequency, that's going to be 1 over J omega C. So if we take the limit as omega approaches 0, which is the frequency of a DC voltage source, we're going to approach 1 over 0. And so 1 over 0, well, if it was 0 over 1, it'd be 0. So 1 over 0 approaches infinity. So this is the reason why a capacitor, anytime we get to a frequency that gets lower and lower and lower and lower and lower, the impedance of it actually skyrockets. It goes up and up and up and up. So to our DC voltage source, it'll be open. And so if there's no current going through R1, it's not effective in the circuit. And of course it can't even reach the AC voltage source, so we don't even need to consider that. So next, what we can see from this DC analysis sub-circuit here is that automatically we'll recognize that this is a voltage divider, and we can just readily write V out DC will be equal to VDC times R3 over R3 plus R2. And that is our DC contribution to our V out. So next, what we'll go ahead and do is we'll take a look at a AC analysis. And so the reason that we draw this sub-circuit to look like how it is because we have, and let me put in where our V out AC is going to be at. The reason why we draw the sub-circuit to look like this is that, of course, to an AC that is sufficient enough in frequency, our capacitor is effectively going to be a short. And so R1 is effective. R3, of course, is still going to ground, but R2 is going to ground also. So what happened to our DC voltage source? Well, what we'd have to do to get a more detailed explanation on that, the bottom line is that to an AC voltage source, the DC voltage source is going to be a short. And here's why. Because if we have an IV curve IV characteristics of a DC voltage supply, let's say we have a value at VDC. That voltage source, if it's ideal and it has no parasitic resistances or anything, if it's ideal, what it'll do is it'll output as much current as it has to output in order to maintain that prescribed voltage. So what this means is that you have a slope here with respect to V. You have a delta V slope here of infinity. And delta I over with respect to delta V, which is changes in I with respect to changes in V, is our conductance. And conductance is related to resistance as 1 over R. So likewise, it follows that 1 over G, our conductance, is R. And so if our conductance is infinity, then the limit is 1 over G G is approaching infinity, which equals R, equals 0. So as the bottom of it gets bigger and bigger and bigger and bigger and bigger and bigger, eventually our value here, which is our resistance, 1 over G is R, is going to approach 0. So the resistance of our DC voltage source to our AC voltage source is going to be 0, which is why we have it shorted and going to ground. So now we will go back to our AC analysis here, and we will take notice that this is also a basic voltage divider as well. And so it will be VAC as a function of time times R2 parallel to R3 over R2 parallel to R3 plus R1 will give us our V out AC. And so by things being superimposed on each other, AC and DC in a circuit, V out as a function of time, since we have AC in there, it's V out is going to be a function of time. Since we have both superimposed on each other, we're going to have V out of T equal V out DC plus V out of T AC. And so, of course, we're going to have VDC times R3 over R3 plus R2 plus VAC of T times R2 parallel R3 over R2 parallel to R3 plus R1. That will be our whole entire expression for our V out as a function of time. It will be offset by this DC amount, and it depends on our the type of sinusoid in terms of amplitude and frequency that we want to put into the circuit. So writing it as a sinusoid, it will be our magnitude there, and then any phase that we have in it. But since it's our reference signal, the phase is relevant because it'll be our defining phase, so we can just leave that out. Now, on the other hand, we have a more detailed analysis of AC depending on how much you want to know about the effects of the capacitance there, because as we can see from our previous relationship of ZC of S being 1 over SC, depending on where we're at with our frequency, we're either going to get more or less effects of capacitance in terms of how much it is scaled up or the amount of phase shift that it causes on the output. So what we'll do is we'll do another AC analysis that is more detailed, that incorporates the use of phasors in order to better understand and get some intuition on what's going to happen. And what you would do is you would crunch the numbers with the phasors, and you'd get an exact number. You'd get an exact amplitude and either positive or negative phase shift depending on the calculation, whatever the calculation yields. So what we would do in that case is, again, we'd have our AC subcircuit. This time we would include the capacitance and so we would have that V out AC is going to be equal to VAC times R2 parallel to R3 over R2 parallel to R3 plus R1 plus 1 over SC. Now, we're going to take this 1 over SC and we're going to write it as a phasor, and we're going to do the same with VAC. With VAC, since it is it's our reference, VAC will have a phase shift of 0 because it's our reference phase for our signal. And so it would just simply be the magnitude of it and then an angle of 0. On the other hand, for our capacitor here, we'll have JWC equals ZC of J omega, and if we multiply through on the top, we get a negative J times J. If we multiply this by, we did J times J, that give us -1, and then we'll have a J on top. So anytime we have a J or an imaginary variable, imaginary component here, what will happen is that that'll be indicated as 90-degree phase shift, and we have a negative here, so it'll be a -90, and so we'll have our capacitive reactance here as our scalar in front, which is just simply 1 over 2 pi Fc. That's our capacitive reactance, or X of C, and we'll have a -90-degree phase shift contribution there. So depending on how scaled up this is how effective it will be here in our denominator. And since it's in our denominator, when we bring it up to the top, it'll actually be plus 90. So we'll experience positive phase shifts, which will shift our graph to the left. It'll shift us over to the left as we become more advanced, is what the contribution of 1 over SC will be, which is just the same as J omega C, or in phasor form, be 1 over C -90 degrees, and our VAC, which is B VMAC by 0 degrees. And so what we'll do now is we'll take a look at this type of a thing on using an example. We'll go ahead and simulate it and take a look at the example and see how exactly varying the capacitance affects this circuit. But we can just see that as the capacitance gets smaller, it'll become more effective. Why? Because if it's 1 over omega C, which is our X of C, then as the capacitance becomes smaller, it becomes more effective. If the capacitance was ultimately going towards 0, the capacitive reactance would get much larger because of it's in the denominator of the fraction. Likewise, if the frequency got lower, it will also have that same kind of effect where the capacitive reactance would be even larger. But let's go ahead and take a look at a simulation and see exactly how the numbers work out.
Okay, so what we'll go ahead on and do here is we'll go ahead and simulate and take a look at our circuit simulation in action. And as we just went over on the board, we see that for our DC analysis, it's VDC over R3 divided by R3 plus R2. We've chosen in this example to make R3 equal to 3 kilo ohms and R2 equal to 6 kilo ohms. After doing the simple math, it comes out to be that we'll have 1/3 of VDC, and choosing VDC to be 3 volts over here, 3 over 3 will be 1. So our DC offset will be 1 volt. Our AC analysis, we will have, as we just went over on the board, we'll have VAC peak times R3 parallel to R2 over R3 parallel to R2 plus R1. In this example, again, we chose R3 to be 3K, R2 to be 6K, and 3K parallel to 6K gives us 2K. And so R1 has been chosen to be 2K. And so 2K over 2K plus 2K is 2 over 4, and 2 over 4 is half. So our peak amount for our VAC will be half of its peak that we have here, and I just set it to be 1 volt peak. So we're expecting to see half of this, because it's going to scale it down by half. We're expecting to see half of that out at as a contribution to V out from VAC. So again, the total net effect is a superposition of AC and DC signals, and so V out will be V out DC plus V out AC, which is a third VDC plus half VAC peak. So again, this will be 1, and then this will have a peak of half, or a peak of 0.5. So we'll expect to see an AC signal of a peak amount of 0.5 offset by 1. And so we'll go ahead and run the simulation and take a look at it. So using the cursors here, we can see down here, cursor 1 is the top one. It's the first row, and we're on channel B here for our output. Our output is the red, and our input is the blue. Our input is taken to be our VAC, and VAC, as we can see, is it's over here, channel A. It has a peak of 999 millivolts. That's 1. If we were to have enough data points, we would get exactly 1, but that's the peak of it, so that's virtually 1. So we have a peak of 1 on our input. On our output, we have a peak of 1.499. So as we can see, it's the vertical scaling is 1 volt per division. So this horizontal here is 1 volt. That horizontal is 1 volt. That's our vertical scaling. And so we can see that there's 1 volt. There's a level of 1 that this is centered about. And so that is our DC offset, and we're getting our 1.5 there, so that's 0.5. So that's what we'd expect, our 1.5. So now for a more detailed analysis, taking into account what type of capacitance value we choose. Well, using the phasors, after we've done some phasor calculations with the entire circuit here, we can see that at 10 microfarads, it's going to be 499 millivolts at 227 positive milladegrees. Positive shifts are to the left, so we would expect, if it was substantial, for it to be shifted towards the left because it's being advanced in time. It's happening earlier, so it would be a shift to the left. And so at 10 microfarads, we don't even have a quarter of a degree, because that would be 0.25 degrees. This is 0.227, just about 0.228 degrees, which is very small. So even though there is actually a phase shift here, it's just so negligible you won't be able to see it just by looking at it. You'd have to calculate it. And we can see here that we have our 0.5 volts, 499 millivolts, our 0.5 right there, included with 1 plus 0.5 is going to give us our 1.5 or 1.499. However, if we have 10 nanofarads, things become a little different, at least with the calculation here, because our scaling of V out AC is going to be scaled down to now 121.874 millivolts at a very large 75.89 degrees, and so that should be very noticeable. So what we're going to do is we have a 10 microfarad value here for this capacitor, and we're going to change it just to 10 nanofarads and see whether or not the calculations make sense in accordance with the simulation. So go ahead and simulate that. And then take a look at it, and of course we can see very easily that there's a large phase shift. It's been shifted to the left, and if we were to say go to its peak amount, try to find where its peak amount is, so I'm going to be looking down here. Seems like about 122 is its peak amount for the AC contribution, so 0.122, and our calculation is 0.121874. If we round that off, that'll be exactly 0.122. So that's exactly what we would expect. And for our phase shift, we could also calculate that out too. I won't do it here, but in order to calculate that, what you would do is you'd make some conversion factors. You would figure out how many degrees per cycle, and then based off of how many degrees you have per cycle, per time period, so how many degrees per time period, then you take the difference of time, and then you use your conversion factor in order to figure out the amount of phase shift between these two waveforms. But for now, we're going to go off to MATLAB next, and it's just extra, but we're going to see whether or not, let me change this back to 10 microfarads. We're going to see, and just check, this is just extra, to see whether or not what we get in MATLAB looks like this for 10 microfarads, and just the extra check on top of what we're doing, because we have some equations and we can just make sure that they check out right. So what we're going to do here now is we're going to look at what it would look like in something like MATLAB if we were to explicitly put the sinusoidal expression into MATLAB and plot it and see what it looks like. So our frequency is 1,000 or 1 kilohertz. That makes our radian frequency, our radians per second, 2 pi f, and I'm going to plot it for a period of 5 times 1 over f. 1 over f is actually the period of the sinusoid itself, but since I want 5 cycles of it, then I'm just going to multiply that by 5, and then this is going to be our time from 0 up to our 5 times our period, and it's going to be in increments of 1 micro tick or bit. So the resolution should be good enough to give us some pretty high resolution of our results. And so here's our 0.5 that we were talking about, that our V out is going to be in, that the AC part of it is going to be 0.5. And then we're going to have our omega times time, and then we're going to have a offset of 0.228 degrees. But since this MATLAB function is in it is in radians, you're going to have to use one or the other, a radian sinusoid or a degree sinusoid. I chose to use radians, and even within that you're going to have to do some conversions, and so I'm converting from degrees here over into radians of positive phase shift. And so our conversion factor is just pi over 180, and so that'll convert it to radians for us there. And here's our offset of 1. So we'll go ahead and run the analysis. Also, this is our input to compare it to, with no phase shift and a value of 1 times it. You can either omit it or you can put it in there 1 times sine of omega times t, and no phase shift at all and no offset, so we're not going to add anything to it. And I just turned the grid on for us, and we're going to see what we get. So as expected, this is exactly what we would expect. We have 5 cycles, 1, 2, 3, 4, 5. This is going to represent time, and this is going to represent amplitude. And so we can clearly see that we have 1 for voltage, a VAC, alternating current voltage source of a level of 1 volt peak. And then for our V out, in our blue here, we can see clearly that we have 1.5. You can also use the cursor here to take a look at it and position it however you want to do so to get different points on the line. But exactly, that's our 1.5, and this is just time here. The x-axis is going to be time. Our primary interest though is our levels here. So again, we can see that there's been a 1 volt offset continuously, and we have our peak value going up from that, from 1 to 0.5, which is our 0.5. And so we've confirmed that through MATLAB. Also, our explicit expression in terms of a sinusoidal expression is correct.